guys, nice to see you. How are you doing? Almost sleeping. So let us recall first what we discussed last time. We considered elastic inelastic collisions. So we need to keep in mind that for elastic collisions, we do not take into account any deformation of the object. And that means that we do not lose kinetic energy. So we have both conservation of linear momentum and conservation of kinetic energy for such system. And for inelastic collision, we do have deformation of the objects, and that results in the fact that we need to take into account transformation of kinetic energy to internal energy of this deformed object, which means we cannot apply conservation of kinetic energy. So with this, we also, during last lecture, we also introduced the concept of center of mass. So we learned how to determine position of the center of mass for a system of many bodies, like individual bodies, or also we considered the case of a continuous body, which of some arbitrary shape. So we also know how to do that. So we can either determine it along one axis in one-dimensional case, or determine position vector of the center of mass. So today we will continue with introducing why this concept of center of mass is important and helpful. So we will consider it in the scope of second law of motion and also in the scope of conservation of linear momentum vector of many body system. And during the second half of the lecture, we will introduce propulsion motion and quantify, derive the main propulsion motion equation, which will relate the velocity of the rocket, for instance, with other parameters which matter for getting higher velocity. That's the goal. You want to provide high velocity for the rocket. And we will see which parameters of this propulsion motion will define the final velocity of the rocket. So with this, we can start our discussion of the center of mass. And first, I would like to remind you how we determine position vector for the center of mass in the case of many body system. So first we have 1 over capital M, which stands for the total mass of the system. And here we have a sum from I equal unity to some capital N, which stands for the number of bodies in this many body system. And here we have product of position vector and mass of individual components of this system, of individual bodies. So that is general equation for our position vector. And now let us make one step in terms of considering the application of this concept. Let's go from position vector to velocity vector. So how do we write? Here we have velocity vector of the center of mass will be equal to what? How we define velocity vector? Derivative of the position vector, like first derivative position vector over time. That's correct. So let us do it. So here we have first derivative of position vector of the center of mass over time. So what we can write here, taking into account the previous equation, that it's equal to 1 over capital M, total mass of the system, sum from I equal to unity, from unity to N, Here will be mi, mass of the individual body of the system, times first derivative of ri vector over time. So this is 1 over capital M sum times mi, sum of the product mi times vi. So here we, instead of first derivative of position vector, which describes position of some body component of the many body system, we replace it with its velocity vector, and we can even put here vector to be consistent. Why it doesn't work? Okay, and now what do we have here? What this product gives us? Impulse. No, impulse, that is about force. So force times interval of the time when it's exerted on the body, that is force impulse. This is momentum, so linear momentum. So in other words, since we have this sum here, it's the sum of all the individual linear momentum vectors of the many body system. So we can write here the following. Actually, let us move this capital M to the left. So it will be capital M times velocity vector of the center of mass is equal to the sum from I equal to unity to N mi times vi vector, and that is nothing else as total linear momentum vector of the many body system. So now looking at this, we see already you're welcome, the value and importance of this concept of center of mass. So in the left side, we have just mass, total mass of the many body system, and its center of mass velocity vector. Here, we may have, depends how many bodies we can have, 10, 100, 1000, whatever, any arbitrary number of bodies which form this many body system. So we have arbitrary number, could be very big number of linear momentum vectors. And what we need to do here, we need to deal with all of them and sum up in order to get the total linear momentum vector of the system. However, we can skip this complicated and time-consuming process because instead of operating with individual bodies, we can switch to the center of mass. If we know position vector as a function of time for the center of mass of many body system, we get its velocity vector, and product to the total mass of the system gives us the total linear momentum vector of the system, regardless of how many components, how many bodies are included into this system. So that's already quite a big achievement, but we can do even more with this. So kind of intuitive next step will be to go from velocity vector to acceleration vector. And in this case, let us express acceleration vector of the center of mass. Obviously, by definition, it's first derivative of velocity vector over time. So that could be written as 1 over capital M. Here will be sum from I1 to N of the product Mi, and here will be dvi vector over dt. Obviously, this term stands for the acceleration vector of individual body in the system. So we can write that here we have 1 over capital M sum from I equal unity to N times Mi AI vector. So now let us again move this capital M to the left. We have capital M times A center of mass equal to the sum I equal to unity capital N Mi times AI vector. So what is this term? It, according to second law of motion, this is force which is exerted, like some net force, which is exerted on component of this many body system with I indexed. So when we deal here with the sum of all these net forces, we get the total force, net force, which is exerted on the many body system. So we can write here, this is the total force, which is exerted on this many body system. What is important here, that this total force includes both internal forces and external forces. So all forces which are exerted on the system. So again, from here we can see that instead of dealing with all these individual forces on each component of the system, we can operate just with acceleration vector to center of mass and total mass of the system. Your suggestion, if we have a many body system, and what will be equal to the sum of all internal forces? So here we deal with both internal and external. But if we sum up all internal forces which act in between the components of the system, what it will be equal to? 0. So, and why it will be equal to 0? Because the internal energy and external, they like. So now we don't talk about external, we have only internal. So we need to recall third law of motion, that there is action and reaction force. So they are equal in magnitude and opposite in direction. If there is some interaction between components of the system, means they will be, some action will result in reaction, they will be in opposite direction, and if we calculate net internal force for this many body system, it will be equal to 0 because according to the third law of motion, they will be compensated. So with this in mind, we can write that the product of total mass of the system times acceleration vector of its center of mass will be equal to the sum of all external forces exerted on this many body system. Since here we have internal also, but the sum of all internal will be equal to 0, so we can kind of neglect with internal forces, like net internal force. So now let us recall how we define change of the linear momentum vector of a single body. So if we have constant force exerted on this body, then change of linear momentum vector was defined as the product of force, which is constant in time, over multiplied by some time interval during which this force was exerted on the body. So this product was called impulse of the force. So we can write now for our particular case, assuming that it may be not constant, this net external force may be a function of time. So in order to get this impulse of the net external force on the many-body system, we will go for integration over time. So we can write here that integral for the sum I equal unity to capital N of all external forces over time according to this equation will be equal to integral of total mass of the system times acceleration vector dt. We can represent acceleration vector as the first derivative of velocity vector over time. So that will be equal to integral. We can already also put out from the integral this total mass of the system, since it doesn't change with time. And here we will have dv center of mass over dt times dt. So we can cancel out this dt and have the following. It will be integral of dv center of mass. And this dv, like integral, will give us some delta v center of mass, which happens in some time interval delta t. So this is equal to delta p total vector, which is the change, so the impulse of net external force exerted on the many-body system. We show that in this case, when we deal with the concept of center of mass, will also be equal to change of the total linear momentum vector of the system. But here, instead of dealing with individual components of the many-body system, we operate only with the change of the linear velocity vector. Now we are approaching to the point when we can ask a question: will the concept of conservation of linear momentum be applicable when we deal with center of mass? So what is the key requirement which allows us to consider a conservation of linear momentum? Can you repeat, please? Okay, yeah, let's say so far we didn't consider time variable mass of the object, which will be next step with propulsion motion, but there is more general requirement. Closed system. So what does mean closed system? Oh, and if they exist, they cancel each other, and we can consider our many-body system as a closed system. So in that case, what it means that the net external force will be equal to 0. So we can write this condition for the closed system. Net external force is equal to 0. So taking this into account and looking at this equation, we can write that total mass of the system times acceleration vector of the center of mass, which is equal to total mass of the system times first derivative of the velocity vector of the center of mass over time will be equal to 0, because this is equal to the net external force. Net external force in the closed system equal to 0, so this is equal to 0. When this will be true, mass is not equal to 0, the system possesses some total mass. Means that this first derivative of velocity vector for the center of mass should be equal to 0. If it's equal to 0, means that velocity of the center of mass does not change. And that is also true for total, like net linear momentum vector. It remains constant. So we can write that total mass times v center of mass, which is total linear momentum vector of the system, in this particular case closed system, is remaining constant. So as you see that the concept of the center of mass, which makes our life quite simpler in many cases, is applicable in the scope of the principle of conservation of linear momentum vector. So that is important information about the center of mass and its application in possibilities to quantify behavior of many body system with just one description of one point with concentrated total mass in this point, and obviously this point should be provided with some time-dependent position vector, and based on that we can get velocity vector and acceleration vector of the center of mass and describe the translational motion of a many-body system. With this, we can make a transition and go to propulsion motion. Actually, this is the case when indeed mass of the object does not remain constant and it changes over time. So any examples of propulsion motion? Obviously, rocket. Yeah, exactly. So that's probably the most common. However, there are other options like some balloon with gas inside, which can just fly away because of exhaust of gas from inside of balloon. So what happens in both of these examples? We have some exhaust of either gas or products of some chemical reactions inside the rocket with certain velocity with respect to the rocket, let's say, and based on the concept of conservation of linear momentum, this rocket, this body, which exhausts the gas, should get some acceleration and gain some velocity. So that's the principle, and we would like to quantify this in the way that we can derive the equation for the velocity of the rocket. Let's try to do it. So we consider some rocket with mass capital M plus delta M. So capital M stands for the mass of the rocket, and we have some amount of fuel which is about to be exhausted. So it moves with some velocity v with respect to the ground. So this velocity v with respect to the ground. Then we have this exhaust of gases delta m with mass delta m with some velocity vector V exhaust with respect to the rocket. So V exhaust is with respect to the rocket. Then, because of this process, the rocket will gain some velocity. So it will be V vector plus delta V vector. And now, based on this system, let us write down the equation for the conservation of linear momentum. So we have what in the initial moment, we have m plus delta m times v, and that is equal to m capital M times new velocity of the rocket, which is v plus delta v, plus delta small m, which is exhausted gas. And here we will have v minus v exhaust. So we have this here, v minus v exhaust, because we need to express velocity of the exhausted gases with respect to the ground. So this is velocity of the ejected, like exhausted gases with respect to the rocket. So there we have this difference between velocity of the rocket and exhaust velocity of gases with respect to the rocket. So eventually these parentheses will give us velocity of exhaust gases with respect to the ground. Now we open the parentheses and see what we get here. Capital M times V plus delta M times V, that is equal to capital M times V. Oh, we don't need vectors here. Then plus capital M times delta V plus delta M times V and minus delta M times V exhaust. So what do we have here? This guy and this cancel out, and also this one and this cancel out. So we end up with capital M times delta V equal to delta M times V exhaust. So now let us consider some limit of delta t approaches to 0. So very small time interval of time when all these changes delta v and delta m will be also approach to very small amounts denoted as dv and dm. So at limit delta t approaches to 0, we can write that delta v approaches to dv and delta m approaches to dm, which will be equal. Any suggestions how else we can represent this small change in the mass, like small amount of fuel which was burned and exhausted in the space, surrounding space of the rocket. So that could be considered also as reduction of total mass of the rocket, because it was exhausted. So that's your point when we have the system with the mass which changes over time. So this gas is ejected and total mass of the rocket decreases. So we can represent this d small m as minus d capital M. So minus stands for reduction of total mass of the rocket. Now, with all this, we can rewrite the previous equation. So it will be capital M times dV equal to V exhaust times d small m, or minus V exhaust times d capital M. And now we can express dV, which will be minus V exhaust times d capital M over M. So our goal is to find velocity, so we need to integrate. So we integrate from V initial to V final, and here we integrate from M initial to M final. So what do we have here? In the left side, we have V final minus V initial. Here we can take out from the integral minus V exhaust. Here we have integral from mi to m final d m over m. So what will be this integral equal to? So we deal with natural logarithm. So let us write here v exhaust equal to natural logarithm of m, and it goes from m initial to m final. So that will be minus v initial exhaust times natural logarithm of m final minus natural logarithm of m initial. According to the properties of logarithm, we can rewrite it as minus v exhaust times natural logarithm of the ratio m final to m initial. And considering this minus, we can flip the argument in the logarithm. So we end up with v exhaust times natural logarithm of m initial over m final. So this is the um, equation which we wanted to know. Now, if we assume that initial velocity of the um, rocket was equal to 0, it just started its launching, so we can write that velocity of the rocket will be defined as exhaust velocity times natural logarithm of the ratio initial and final mass of the rocket. So now let us look closer to this equation and think about it. So we want this velocity to be as high as possible, and there are several options to do. So obviously here we have linear dependence of rocket velocity on exhaust velocity. So any suggestions how can we increase the exhaust velocity? This is exhaust velocity. If I ask you how we increase the velocity of the rocket, that's another question. But we know that we can increase velocity of the rocket if, like first option, if we increase this value. So we increase exhaust velocity. The question is, how do we increase? What has to be done in order to increase exhaust velocity of these gases? Okay, that's the right answer actually. So what we need to do? We need to increase temperature of these gases which are ejected. So if we increase energy, the kinetic energy of these molecules, which are products of the uh, like burning of this, what actually happens there is oxidation of the fuel inside the rocket engine. So we want to produce per unit amount of burned fuel as much energy as possible, which results in increased temperature of this exhaust gas. If this temperature increased, the pressure inside the rocket engine increases, and obviously the velocity of exhaust gases will increase. So development of new types of fuels which generate more heat per burning unit of mass of this fuel. And also we need to develop quite efficient oxidizer, because keep in mind that rockets are traveling in the space. They do not um, use air as a source of oxygen, and even this short time when they travel in atmosphere, the amount of oxygen which can be provided from air is limited. So you need to have a combination of fuel with oxidizer. So it's either solid fuel rocket engine or liquid fuel rocket engine. In both cases, we have a combination of fuel itself and oxidizer. Let's say it's quite possible for liquid um, type of fuel engine to use liquidized oxygen. So we cool oxygen to that extent that it becomes liquid, and then provide liquid oxygen in the rocket engine together with the fuel in order to get the highest possible oxidation inside this engine with regardless of external conditions. Either we have atmosphere or we are somewhere in the space. Uh, which challenges do you envision when we increase temperature and increase this exhaust velocity? So this, yeah.
The temperature of the liquid oxygen, does it affect the overall heat?
Well, that is good question. So actually what happens that this low temperature of liquid oxygen is used in favor for the system, because with that you try to solve the challenges which I was about to mention. If we increase temperature in order to raise this exhaust velocity, then keep in mind that the engine should be made of some materials. It's not just burning somewhere in space, open space. So these materials should be able to withstand this extremely high temperature. So we increase temperature, and that is good for the rocket to move, but we don't want this rocket to be melted on the way. So in order to handle this high temperature, we need advanced high temperature resistant materials, which will be embedded into this construction of the engine. And second, use some approaches in order to cool down the housing of the engine while keeping the temperature of the burning region as high as possible. So this oxidizer, which is liquid oxygen, goes through some channels in the housing of the engine as a cooling liquid before it's injected into the burning area of the engine. So that is how we take off, like dissipate external additional heat from the housing of the rocket engine by cooling it with liquid oxygen, and then use this already warmed up oxygen in burning of the fuel inside the engine. So this combination of material science and mechanical engineering in this case provide possibility to increase as much as possible the burning gases temperature and achieve very high exhaust velocity. So there is another possibility which is shown in this equation. We can also increase the ratio between the initial and final mass of the rocket. What does it mean? If we want to make it larger, So we want to make this initial mass as big as possible. And that means we want to fill the rocket with respect to final mass. So that means we want to fill the rocket full with fuel and oxidizer. So it will be like 0% of the volume of the rocket left for some useful load. Yes, obviously we will get the maximum velocity for such system, but then it's useless because we want to send some astronauts or some goods to International Space Station. So part of this volume should be occupied with some useful goods. And obviously there will be some compromise between amount of fuel which we provide to the rocket and amount of useful load. We need to find a compromise ratio. But obviously we see from here that in order to get the highest velocity, like final velocity, we need to burn maximum amount of fuel. So now let us recall previous equation which we got in this during this derivation. It was capital M times dV equal to minus V exhaust times d capital M. So that was this initial form of differential equation which we got. And let us divide it by delta t, like left and right side. So here delta t and here delta t. So tell me, what is this left side? Force. So it's actually the driving force exerted on the rocket, means propulsion force. So we can write this force is equal to M, capital M, times dV over dt. And what is nice about this propulsion motion, since we have system with changing mass over time, we can represent it as follows from this equation: as an absolute value of the exhaust velocity times first derivative of the mass of the rocket over time. So again, looking at this equation, we see that the propulsion force which is supposed to accelerate our rocket, which we want to be as high as possible, will be proportional, linearly proportional to exhaust velocity. We already mentioned that is important parameter in both equations. So we want to increase temperature of burning inside the rocket engine. However, we have here one more parameter, and this derivative of the mass of the rocket over time stands for the rate of burning. So it tells us how many kilograms of fuel is burned, like together with oxidizer, is burned per unit time. And this rate of burning together, high rate of burning together with high velocity, exhaust velocity, provide high propulsion force, which accelerates the rocket. Since you may see when these rockets are launched at the like zero, so the zero velocity, ground level, they start to launch, like huge amount of energy is released in this form of excessive fire exhausted from this very hot gases exhausted from the engine. And since we want to provide both very high temperature and very high burning rate, in order to protect the concrete construction of the launching table for the rocket, tons of, like thousands of tons of water is provided during this very short time when these exhaust gases are still in contact with the concrete table. They like pump a lot of water in order to protect walls of this concrete table from being damaged by these extremely high temperatures and extreme pressure provided by very high burning rate. Otherwise, if you don't provide this kind of buffer layer created by huge amount of water, this concrete table regardless of the quality of the concrete, will be damaged, and you will have extremely expensive rocket launch because that will be just single use, which is not acceptable in the space industry. So, summarizing our today's discussion, so we continued with the concept of center of mass. Consider the center of mass concept in the scope of second law of motion and principle of conservation of linear momentum. We have shown that it's indeed a nice approach which can make our life easier when we don't need to deal with um, individual linear momentum vectors or force vectors exerted on individual components, bodies of the many body system. Instead, we deal only with one point, with concentrated total mass of the system in this point. And what we need to do initially, we need to define the position vector as a function of time for the center of mass. Then by taking first and second derivatives over time, we can go to velocity of center of mass and acceleration of center of mass. Also, we introduced the propulsion motion principles and derive the general equation for velocity, like propulsion motion, which defines the velocity of the rocket as a function of exhaust velocity of gases and ratio between initial and final mass of the rocket. So eventually what we can claim for the propulsion force, we want very high exhaust velocity means high temperatures and very high rate of burning, d capital M over dt, which shows how fast the mass of the rocket is reduced because of exhausted fuel and oxidizer. So thank you very much for attention. Have a good weekend and see you on Monday.